Well, it's that time of the year again where we have a date. I thank you all for coming. As you all know, I keep saying every year, the only reason we keep doing this is because you keep coming. And the reason you keep coming is because we live in an amazing community with folks like you that are interested in education, and we're interested in giving you what we can. So thank you. I think it's just Tucson is just the best place in the world. This whole experiment started 11 years ago when we gave the first lecture on that first lecture series on evolution. We expected at that point that we would have 100 people out there with pancards saying against or for, and that didn't happen. And in fact, everybody showed up and was interested in what was going on. So that showed that we had something going. And the second lecture series was global climate change. 10 years ago, we gave a lecture series that described what we understood about global climate change at that time. There was still a lot of commotion as to whether we really existed or really didn't exist. Even then, the consensus of the scientific community was that it was certainly happening, but that we really didn't understand what the consequences would be. 10 years from then, today, we decided to do it again because we clearly just had a big event in Paris describing where we're at, and because even though we still don't quite understand all of the consequences of global climate change, we can already see very straightforward many of them. In the case of southern Arizona, all the models show that we're going to be the bullseye of the US. The bullseye means we'll be warmer and drier than almost anywhere else, and we all have to deal with that. Now, the lecture series is not going to be all doom and gloom. It will describe what we understand of the lectures of global climate change, and then it'll describe, in a few of the lectures at least, what we are trying to do about it. So the idea then is that if you're ever asked to vote for whether we should get water from somewhere else or here or whatever, you'll have at least enough in you to be able to vote somewhat intelligently. That's the reason for these lecture series. Much of what we do now is much of what drives the way we live is driven by technology, and it's driven by science. Many times we're asked to worry about them or to think about them. We don't really know how, and we hope that we can bring some of that education to you. The lecture series is an expensive endeavor, even though none of our faculty members charge a nickel for doing this, and they work very, very hard. The bottom line is that we have publications to put together, and we have to rent this place, and we have a lot of stuff to do. We stream it. We have great partnerships with Arizona Public Media, but all of this costs a fair amount of money, and it is the folks that support us that allow us to do it for free. We had some very powerful partners in the past and in the present. Tucson Electric Power and Ventana Medical are the lead folks that make this happen, and I would like to ask everybody to give them a big round of applause. The Arizona Daily Star has been just an amazing partner with the College of Science since day one, and I think for those that read the newspaper yesterday and we're careful not to throw the inserts out. We were one of those inserts, and importantly for all of you to know is that those inserts are not driven by the marketing department of the Arizona Daily Star, but they're actually driven by the editorial part of the Daily Star. So they're peer-reviewed, and it's the science that's going on here, and it's a beautiful publication that we do for two reasons. One of them is to show what we're doing to all of you, but also so that we have a document that can be used in K through 12 as we try to educate students, and that they know how to connect to various people at the university that are doing STEM, science, technology, engineering, and math. With respect to that, those individuals that support us also support the fact that we can get teachers from K through 12 community to come and take courses with us and take the curriculum back to class so that the curriculum that our students get in middle school and high school are up to date. John Pollard, who's a faculty member in the chemistry department, is the individual that sort of connects us with the teachers from middle school and high school. And I'd like John to stand up, and the teachers from middle school and high school that are here to further their education so they can further the education of our own students. And this year, thanks to the great support from the provost office, we've always recognized that as beautiful as all of you are, you look about as like I do. And the students from the university are not here. And clearly what we're producing is, some stuff that they should be paying attention to. So this year, there's been a big program going on. John Pollard is also in the middle of that. But in the energy, environment and natural resource building, which is on 6th, it doesn't matter where it is, it's right across the street. We have about 500 of our own undergraduate students listening to the lectures. And we also have programs with the Honors College and all throughout the university so that they can actually partake of what we're so proud to produce for all of you. So that's a great improvement. And I just wish to remind all of you that the lectures, the 11 lecture series from the past, are on the web, and you can access them, all the podcasts, again, through the partnership that we have with the Arizona Public Media. And if you're interested in showing them in some party in your community, give me a call and I'll show up and I'll answer questions as best as I can. Now, I want to thank all of the individuals listed here, in addition to I already mentioned Tucson Electric Power and Ventana Medical, for their support to the lecture series. And at this point, I would like you to give all of them a round of applause because they've been extraordinary. So, the lecture series, it starts today with what we know about the oceans and what is the control of the oceans in global climate change. After that, we will talk about atmospheres. After that, we will talk about how all of this impacts the biosphere. We'll talk about how global climate change is changing patterns of disease. And then we go into the engineering. So we'll talk about what we're trying to do to deal with it, to ameliorate it, and to make the emissions that we have today less so that it's not as bad as it would be otherwise. And that's what the Paris talks were a lot about. And finally, we'll have a lecture, the last lecture, we'll try to put all that together in how these lecture series how the global climate change affects civilization in general. Now, many of you may have heard of a term that's called the Anthropocene. It's a term that is being used more and more, and it really sort of represents a time in which many scientists are arguing that humankind has been affecting geologic processes more than anything in the past. There's been a big debate in some communities that the Earth has been colder and has been warmer than it's been today when there was no humans around. So we know for a fact that the Earth can change. And if you look at this is 4.5 billion years of evolution, and geologists have actually sort of put boundaries between various times. The most famous of them, of course, is the Cretaceous-Tertiary boundary, when all the dinosaurs died except for our good old purple dinosaur in the movies. But in the end, there's geologic periods in which have been catastrophic. The Cretaceous-Tertiary one is one. The Permian-Triassic period was one in which about 99% of all the species died. We don't exactly know why. But in all of these cases, geologists have been able to pinpoint at the rocks, at something in the rocks that allows them to go from one period to another, from one epoch to another. Sort of, you want to call it a golden spike. In the case of the Cretaceous Tertiary, it's a layer of soot that is all throughout the world that's used as where that boundary exists. It's a boundary in time. And in other places, it's the loss of a particular fossil and so on. What's important about all of these changes in the past that people have to recognize is that in the past, all these changes have had a rate that would be called geologic. In other words, it doesn't happen instantaneously. It doesn't happen in the time that we see happening today in the Anthropocene. Geologists and stratigraphers, the stratigraphers are those that actually name all these things, still have not approved the term Anthropocene because they're trying to figure out exactly where it starts. They're trying to figure out that if you were now a geologist 2 million years from now, where would you actually put your pencil to say this is where the Anthropocene begins? But the Anthropocene is a time where the rate of geologic change is truly beyond anything we've seen any other time in the geologic history. So even though, in fact, the Earth has gotten cooler, and then there's been times where the Earth has been completely solid ice, and there's times when the Earth has been warmer. In fact, when the dinosaurs were around, the Earth was way warmer. We know all of that. Geologists have known all of this forever. We've been able to relate them sometimes to volcanic activity, sometimes to erosion, which causes, when you erode, rate of erosion causes how rocks actually change the mineralogy, and that changes CO2. What is always the case is that temperature is related to CO2 throughout the history of the Earth. And I'd like to show you now a little film that talks about the Anthropocene and why it's such a dramatic period in geologic history.
This is the story of how one species changed a planet. The latest chapter of our story begins in England 250 years ago. Fueled by coal, then oil, several brilliant inventions appeared. They ignited the Industrial Revolution, which spread like wildfire through Europe, North America, Japan, then elsewhere. The great railways, then cars and highways, connected people across the globe. Medical discoveries saved millions of lives. New artificial fertilizers meant we could feed more people. Population rose rapidly. But this was nothing compared with what was to come. The 1950s marked the beginning of the Great Acceleration. Globalization, marketing, tourism, and huge investments helped fuel enormous growth. People swarmed to cities, which became even more powerful engines of creativity. In a single lifetime, the well-being of millions has improved beyond measure. Health, wealth, security, longevity. Never have so many had so much. Yet 1 billion are malnourished. In a single lifetime, we have grown into a phenomenal global force. We move more sediment and rock annually than all natural processes, such as erosion and rivers. We manage 3/4 of all land outside the ice sheets. Greenhouse gas levels this high have not been seen for over 1 million years. Temperatures are increasing. We have made a hole in the ozone layer. We are losing biodiversity. Many of the world's deltas are sinking due to damming, mining, and other causes. Sea level is rising. Ocean acidification is a real threat. We are altering Earth's natural cycles. We have entered the Anthropocene, a new geological epoch dominated by humanity. This relentless pressure on our planet risks unprecedented destabilization. But our creativity, energy, and industry offer hope. We have shaped our past. We are shaping our present. We can shape our future. You and I are part of this story. We are the first generation to realize this new responsibility. As the population grows to 9 billion, we must find a safe operating space for humanity. for the sake of future generations. Welcome to the Anthropocene.
And now I'd like to introduce tonight's speaker, Joellen Russel. Joellen Russel is an 1885 Society Distinguished Scholar and an Associate Professor in Geosciences. There she is, with a joint appointment in Planetary Science and the Lunar and Planetary Laboratory. Joellen uses global coupled climate models and Earth system models to simulate the climate and carbon cycle of the past, the present, and the future, and develops observational-based metrics to evaluate these simulations. She is one of the 14 scientists behind an amicus curiae brief supporting the plaintiff in the historic 2007 U.S. Supreme Court decision on carbon dioxide emissions and climate change. In 2011, the American Association of Petroleum Geologists appointed her a distinguished lecturer. She currently serves as a member of the United States Carbon Cycle Science Steering Group and the World Climate Research Program Southern Ocean Region Implementation Panel. Her research publications have been cited more than 3,000 times. She teaches over 900 students in oceanography and climate every year, for which she was awarded the UA Provost General Education Teaching Award in 2010. Her degrees include an AB in Environmental Science from Harvard, a PhD in Oceanography from Scripps Institution of Oceanography, University of San Diego, and it is my absolute pleasure to introduce a colleague and a friend, Joellen Russel.
You have no idea how much I love being introduced by Joaquin, who is, of course, a colleague and fellow professor in the best geosciences department in the country, right here at UA. So I'm going to talk to you today about the ocean's role in climate, heat and carbon uptake in the Anthropocene. Let me see, is this not quite, okay. So this is the pale blue dot. It's a picture taken by Voyager in February 14th, 1990. And when Carl Sagan's, what he wrote about it was, like it or not, for now, Earth is where we make our stand. This is it. This is our home, right? The only one we've ever had. And it's blue. It's beautiful blue. I grew up in an Eskimo fishing village 31 miles above the Arctic Circle in a tiny village called Kotzebue. Some of you may have heard of it because it was where the president went to visit and was all worried about the bathroom facilities. But that's where I grew up. And in fact, it's where I decided I wanted to be an oceanographer, because I looked at Sally Ride's picture on the cover of Time magazine, and I knew I wanted to be an explorer. But that pale blue dot looked lonely, and I just couldn't leave, so I became an oceanographer. Seriously, I've been dreaming about being an oceanographer my whole life. And oceanography has always meant I've spent about a year of my life at sea. This is not responding very well. I've spent about a year of my life at sea making measurements in the Southern Ocean, in usually the deep winter, with seas you can't really imagine unless you've been there. 300-foot boat, right? Great big huge boat, you know, chug, 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 up the side of the wave, and then shush down the other side, like you're skiing, almost 0 G, I'm not kidding. Then whoomp, you dig the prow into the next great big huge mountain of water, which then proceeds to fall on you. And it presses the ship down so far that she shudders and shakes and kind of jerks to get back up to the surface. Oh, I still have really bad nightmares. I think I have a little oceanographic PTSD. No, really, it's very hard work. So when I finished my PhD, I actually went into modeling and the atmosphere. And it's not because I'm a wimp. It was because I couldn't make enough measurements by hand from a ship in order to capture the change we were seeing in the ocean. The ocean was changing so quickly over space and time that we needed more measurements, not just 10 more or 100 more, thousands and thousands more in order to tell what was happening. So One of the reasons, let's look at this now. So this was this great article in the New York Times, and I love this picture because here we have the whole planet, and it's all warming except for a little bit around Greenland, and this huge area around Antarctica. And I'll tell you why. It's not because there's not heat going in here. In fact, the Southern Ocean is where most of the world's heat has gone. I'm not kidding. But if you want to look at the actual atmospheric temperatures, here they are. This was a record by more than 0.2 of a degree in 2015. Really. And 2016 is already still warm. But here, if you take nothing else away from this talk, global warming is really ocean warming. So we have the ERBE. ERBE's my bud. ERBE is the Earth Radiation Budget Experiments, which is a series of satellites that looks out at the sun and in at the top of the atmosphere. And what ERBE tells us is that every single year there is an energy imbalance. More comes in than goes out. More every year. This is what's driving the warming. But the problem is this tiny little purple line that I bet if you're in the cheap seats you can't see, that is the atmosphere. That's the warming in the atmosphere. It's tiny. It's 3%. The 93% is going into the ocean with a little left over to melt some ice and warm the land. Global warming is ocean warming. The energy did not leave the Earth system. It's been absorbed by the ocean. This is a really big deal. Let me show you. Okay, so everybody says, so how do you know it's really warming? Well, it's not just the atmosphere. Like I showed you, it's kind of the smallest part. So here are all these indicators. This is from the IPCC 2013 summary. This is 5 data sets of summer Arctic sea ice extent, where we're getting decreases, glacier mass balance decreases, northern hemisphere snow cover decreases, and then increases. Humidity, ocean heat content, tropospheric temperatures, land surface air temperatures, and these are 5 data sets, 2 data sets, 6 data sets. Basically, we're seeing it everywhere. The signs are everywhere you want to look. But I want to talk about the ocean. So, does this need a new battery? Because it's just not advancing. Seriously, it's just not advancing when I click on it. So the Southern Ocean and the deep ocean are warming. So remember when I said it looked like there wasn't any surface air warming down around Antarctica? What was that all about? In fact, this is the deep ocean around 4,000 meters down. This is 40 football fields down in the ocean. 40 football teams. This is the deep black abyss. It's far, far, far black, black, black. And the red ketchup that you're looking at, the gray is the continents. We're looking at it. This is an oceanographer's plot, as you can tell, because the oceans are lit up and the land is all, okay. So it's warming all the way around Antarctica. Why? Why is so much heat going in around Antarctica? Because the ocean is mixing, and it's mixing more than we expected it to, more. In fact, maybe even much more. So I'm going to give you a brief CO2 primer. What does carbon dioxide in the atmosphere do? What does carbon dioxide in the ocean do? Let's just get past this. So the greenhouse effect. Some of the infrared radiation passes through the atmosphere, some is absorbed and re-emitted, and some of it is emitted from, as it's emitted back from the Earth's surface, some of it is re-radiated by greenhouse gases, and they include water vapor, CO2, methane, nitrous oxide, and some others. This is what it looks like in the atmosphere. This is what the record looks like. We're looking at 1960, actually 1958, and we're looking at the record of Mauna Loa and the South Pole. And these records were started by this guy, Dave Keeling, who is really a climate hero. This guy, you have no idea. He was a professor at Scripps, where I did my graduate work, and one day at the picnic tables down in front of the beach, there were no other seats. There was just this one guy sitting all by himself, and I thought, well, okay. And I plunked myself down and pulled my brown bag out, like his, and he said, so what are you working on? And I told him, and he said, yeah, I do a little CO2 work. It was Dave. It was Dave. This guy actually he visited my parents. I mean, he was wonderful. I miss him. But he did this extraordinary work. There were years, where NSF actually the National Science Foundation actually pulled his funding. And he had no money, but he kept making the measurements and told Scripps to pay people and that he would find it somehow. And in fact, eventually, they made it up. But they tried to stop him from doing this, which is extraordinary. So you see the increase in the CO2. If I took the trend away, what you'd see is the seasonal cycle and CO2 associated with the growing of green things in the spring and the summer, and then the dying and decaying and release of all that CO2 back to the atmosphere in the winter. If I took the seasonal cycle out, what you'd see is El Nino. Now, I know you can't actually see El Nino. All you can see really out in the cheap seats is probably the trend. Maybe if you squint, you can see the seasonal cycle. On top of that is the El Nino variability, and if you took away the El Nino variability, you would finally see volcanoes. This is how we know what causes CO2 increase in the atmosphere. We know exactly. Okay, so this is the Global Atmospheric Carbon Monitoring Network. It started with those 2 stations by Dave Keeling and now is all over the world. And what's amazing about CO2 is that it's a very well-mixed gas. This is the southern hemisphere at 90 south. You can see it increasing in the southern hemisphere. This is the increase in the northern hemisphere with a little more variability because we have more land and more land plants doing the seasonal cycle thing. But you can see where we have ended up, well over 400 parts per million. 400 parts per million. It's been millions of years since we've seen 400 parts per million. It's a big deal. All right. So here are the carbon emissions since 1950 for our big emitters. Okay, everybody thinks we're the #1, but we're not even close anymore. China is the biggest emitter. And what's even more extraordinary is that the US is actually 10% off our peak emissions. And we did that since the recession while we were growing our economy. The US has already proved you can grow your economy and emit less carbon at the same time. We've already done it. Yes, yes. I knew you would understand how I feel about this. I have hope. It's amazing. You have to imagine, I've been looking at this for 2 decades now, watching this, and now we're making progress. Okay, so here is the perturbation to the carbon cycle. We're seeing a big ocean sink of almost 10 petagrams of CO2 per year into the ocean. We're seeing a land sink with a big uncertainty, some land use change, like, deforestation, that's basically adding more CO2 to the atmosphere, and there's a big atmospheric growth, which is, of course, what's driving our warming. Okay. So here's where it went into the ocean, and you'll see 2 things. We've got a very carbon-rich North Atlantic, and we've got a very carbon-rich Southern Ocean. This is the column inventory. If you're actually looking in the ocean, how much of the extra human-made CO2 has ended up in the ocean. And I'm going to tell you something about how the mixing is working, that it's been so specifically these places where the CO2 has gone in. Next slide. Okay, and I did want to do a shout out that the University of Arizona has been in the oceanography business for a long time. Some of the best results we have for what happens when we put this much CO2 into the ocean, the carbonate ion concentration decreases with the increase in our emissions. You see here's 180 ppm, 280, 380. Of course, we're in here now at 400 plus. At doubling of CO2 at 560 and at 3 times CO2, when we get to that level, we get net dissolution. That means all the calcium carbonate-bearing organisms, things like sea snails, little pteropods. We've already seen mass death in the Southern Ocean around Antarctica of these guys. Foraminifera, they also made them look like teeny weeny little popcorn, and they're the base of the food web in the ocean, the primary producer. And we also, eventually, if you have grandchildren who haven't seen the Great Barrier Reef, I would take them sooner. I would take them sooner. No, really, it's sad and it's awful, but those CO2, the CO2 in the atmosphere dissolved in the surface water forms carbonic acid, which is essentially we're titrating the ocean. Even if we could get it to cool down, we would still have all the CO2. It's very serious. Okay, so that's my CO2 primer. Oh, and here's some great shots. So experiments on many scales. These were actually done, those experiments were done in the Biosphere 2 ocean. And Julie Cole is in the process of actually reviving the research purposes in that ocean. I'm so excited about this. So I'm sure there'll be web stuff and all kinds of cool things soon. So check it out, oceanography at UA, woo! No, this is really important. Okay, so why is the Southern Ocean important, and why do we work so hard to get it right? Because so much of what's going on in the global ocean is happening around the Southern Ocean. I happen to be obsessed because of those first cruises I went on when I was 22, 23, 24, and I had never felt wind like that before in my life, never seen waves like this. I was totally hooked. Oh, I have to know what's going on here. And the problem is it's complicated and it's big. It's not just one thing. We have huge westerly winds that roar around the open ocean around Antarctica with no barriers, right? Roaring around. They're 30% stronger than the southern hemisphere, than the northern hemisphere winds that we experience. 30% stronger. Because no speed bumps, no Rocky Mountains, no Himalayas. This is just all there is. So it pushes the water, because of the Coriolis force, away from Antarctica in all directions. And since you can't have a hole in the ocean, up the water comes. I remember putting in my dissertation that I thought the water, from my measurements, et cetera, were coming up from about 1,500 meters, a kilometer and a half to 2 kilometers. And there was huge argument on my dissertation committee that maybe that was too much. And now we know that it's coming up from much deeper, 3 kilometers, where actually the wind's so fierce and it's pushing it away so much that the upwelling is coming up from the very abyss. And it's amazing because that water has not seen our new human atmosphere, has not seen that warming, has not seen that CO2. So the potential is this very cold, never seen the CO2 water before, to take up CO2 is huge. It's extreme, and that's what it's doing. So the Southern Ocean around Antarctica accounts for 67 to 98%. That is not a misprint. That actually comes out of the global Argo array of profiling floats for temperature and salinity. So 67 to 98% of all the heat that goes into the ocean goes in around Antarctica. That's how much. That's why we study it. It's so important. This is a great paper by Dean Remick that came out just this last May. Second, it accounts for up to half of the annual oceanic uptake of carbon dioxide. So the Southern Ocean, this little patch around Antarctica, is actually helping us slow the rate of total warming that we're experiencing in Tucson and Phoenix, partly by directly taking up the heat, and partly because it's also taking up the CO2 that would otherwise be in the atmosphere, making us hotter. So I love to give this public outreach talk that is how the Antarctic helps Arizona keep its cool. It's really important. Everybody thinks it's all about what happens here, but in fact, we depend on what's going on around Antarctica. And number 3, and this is something people don't think about, the vertical exchange, all that up and down that we've been talking about, is responsible for supplying plant food, nutrients, to the global ocean, because it comes up and then some fraction gets pushed away, and it sits underneath the growing photic zone all over the world. This water that comes, this Antarctic intermediate water, basically upwells to fertilize the global ocean. 3/4 of all the biological production would turn off if we didn't have this nutrient resupply from the deep ocean. So the Southern Ocean is really where it's at. And by the way, the reason I really think hard about the biological production is because in developing countries, many of them, the percentage of the total protein that they consume is much higher from marine sources than it is in our country. So 20, 30, 40% of all the protein they consume, at least the Millennium Project tells us, is marine-based. So significant changes to this exchange could have huge impacts on food supply for some of the most vulnerable people on planet Earth. So this is just I'm giving you a cartoon of what the atmospheric circulation goes. So when I'm telling you about the westerly winds down here being outrageously strong, and we benefit from our westerlies whenever we get a nice storm coming through in the winter. Isn't that great? And of course, we sit right here in the dry zone in the northern hemisphere. But let me just show you what it looks like on an actual planet. So if you were an alien in a spaceship, this is what it would look like. This is real data from that's been made into this great animation at the University of Wisconsin-Madison. And what you see are these westerly winds ripping along here in the south, ripping along here in the north, and then this poof, 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 poof of the convective plumes that are occurring in the tropics. So that cartoon that I just showed you with our convection in the tropics and our westerlies, that's actually really, even with the naked eye, you can see that that's basically the circulation of our atmosphere. And the trick is the westerlies are changing. They are changing. So the westerly winds from our big climate model simulations, this is from the IPCC 2013 report, are projected to shift poleward. And we've already observed this. We are drier, we get fewer storms in the winter, and we are warmer because our westerlies have moved poleward. So basically Northern California and Southern Oregon are getting some of the wet that we were expecting. And it's hard to eat. Nobody sells farmland in Saskatchewan anymore, up near Saskatoon, because they can lease it out for 8% a year, because they're not getting enough water to actually have dryland farming be very successful. And it's because our westerlies are shifting poleward in both hemispheres. And this poleward shift, we observe it already today, but the trick is more CO2, and this is North America, this is North America, this is North America. This is under we aggressively reduce our emissions scenario, and this is our burn it all scenario. So here is an aggressively reducing our emissions, where in the southern hemisphere, those winds are still likely to move poleward. Still, even under an aggressively reducing our emissions scenario. And in a burn it all scenario, we completely change the plumbing over Antarctica and the Southern Ocean. It's a really dramatic change. So, and what do we not like about this in this scenario? Of course, see the blue, fewer storms, see this part of North America, right? Yeah, that's where we live, just by the way. This worries me too, because this is my home now. I don't know about you, but I have two little kids, 5 and 8, and in the summer when cabin fever season hits, I'm just like, oh, please, dear God, school has to start soon. I love them dearly, but I can't just throw them outside because it's too darn hot. Okay, so why are these westerlies moving? Well, there's actually two explanations. They're both, unfortunately, human-made. So when the ozone hole was ripped open because we had ozone-destroying chemicals like freons that basically destroyed the ozone in the stratosphere, which then allowed, when we had photons and we have a nice ozone layer, it hits a photon hits a molecule of ozone, it breaks apart, and when it reforms, it actually releases heat. So anytime you had photons and ozone, you'd end up with a warmer stratosphere. No ozone, colder stratosphere. And so early on, it was because we cooled our stratosphere. So right around, the last 20, 30 years, we've had poleward shifting winds because the ozone hole made it cold in the stratosphere and the troposphere, was slowly warming. Now in the future, even if the ozone hole recovers, which last year was the biggest ozone hole ever around Antarctica, not hailed yet. I keep waiting for it to happen, but it's pretty ugly down there still. So even if the ozone hole recovers, the warming in the lower atmosphere, the troposphere, where all the CO2 is going to basically force those winds poleward anyway. So poleward shifted winds started out driven by ozone forcing and will continue because of the increased CO2 and the increased warming in the lower atmosphere. So here are two different models. And this is work I did with Ron Stauffer. It's actually he's the lead author on this. And he's here in the audience from the Geophysical Fluid Dynamics Laboratory. And so if I make any boo-boos, it's all his fault. No. I'll keep my boo-boos. That's okay. But this is it's a paper we co-authored together when I was at GFDL. And what it shows is that with each of these models really have one difference. The solid line model has a poleward shifted wind, like we're expecting. The dashed line model has an equatorward shifted wind, like we used to have. And essentially, when you have a poleward wind shift, the ocean takes up way more heat. Whereas the only difference here is really that we had an equatorward shifted wind, which took up much less heat. So in fact, by pushing the westerlies poleward, we've actually increased the amount of heat the ocean takes up. And if you'll notice, the difference between the green scenario, which is increasing use of clean energy, versus the B1 population peaks, the difference here is almost negligible, the difference because the ocean is such a big driver. Okay, so simulated ocean heat uptake. US temperature and precipitation. This is from the same kinds of projections. This is an ensemble mean of a whole bunch. And what you'll see is the temperature are projected to where we live. Joaquin was right. We're right in the bullseye. And here is the precipitation decrease. Those poleward shifted are basically going to make us drier. And we were already going to be hotter. So imagine that if you were growing crops here and you were trying to calculate how much more water you'd have to pump and how much that would cost, you'd have to think about, well, one, we're going to get fewer storms, and two, we're going to have more evaporation. And Dave Battisti is coming next week to talk to you all about atmospheric changes and food security, actually crops, and what this means. So come next week, because he's awesome, and it's really important. You can do these calculations now. Just, can we get it? All right, so I need to tell you a little bit about models, because this is how we tell when we don't have observations. What happens next? We don't have any other crystal ball except math and supercomputers. I know that sounds crazy, but this is actually how we see the future. And it really matters that we get these right, because it could be the difference between projecting that, oh, it's, business as usual, it's okay, and wow, our children will suffer if we don't hurry up. Okay, so climate models are just computer code that solves differential equations of air motion and thermodynamics to obtain time and space dependent values for temperature, wind speed, etc. Basically, this is what I always tell my kids, is like, that's it, Mama works with math and supercomputers and I can see the future, woo! And that's actually what we're doing. We're really, all we use is incoming solar radiation, total amount of carbon in the system, total amount of water in the system, the size of the planet, and the rotation rate. Oh, okay, and the topography. Yep, no, really, that's it. It's amazing. So, and just by the way, we have an amazing facility here that allows my graduate students and others across campus to actually run these Earth system models and climate models right here at the University of Arizona. The cutting edge right here, and it's this UA Research Data Center. The university has made some very wise investments in this area, and it's just been fantastic. I might add that a really serious chunk of the size of this research data center is from faculty buying in. We're known for being an amazingly collegial campus, and this is one of the best evidences of it. We have great facilities because it's a partnership between our administration and our faculty, and this is amazing. All right, let me show you what we did with it. We're having technical difficulties. Is there anything we can do with this? Because it's just not working at all. So, I'm sorry. I'm used to this because I teach really big classes. So an Earth system model closes the carbon cycle. A climate model just has the physics, the atmospheric circulation, the sea ice, the ocean circulation, the land physics, and hydrology. Can we advance? Sorry? Yeah. So the Earth system models actually close the CO2 budget, which is amazing. We didn't even have these 5, 6 years ago. These are new, where we allow the CO2 to be interactive with plant ecology and with ocean ecology and biochemistry. And I'm not going to show you any equations, but I want to just show you. This Elena Shevlikova is amazing. She's one of my very good friends, and she wrote the dynamic vegetation model at the Geophysical Fluid Dynamics Laboratory, and this is her land model, and it's beautiful. Let's go to the next one. And this was written by John Dunn, who is an ocean biogeochemist and modeler at GFDL, and he wrote this as our ocean biogeochemistry model, and it is also amazing. He's basically they've taken what is most essentially important about the ocean biogeochemistry and most essentially important about the land dynamic veg and put them into these equations, which allow us to solve our full carbon budget. Is it? Oh, okay. All right, so let's test the models. Let's see. So we've got these fabulous new Earth system models with all these bells, whistles, and gizmos. So can we actually see better about this picture? Can we actually get these different pieces and metrics for them? So this is some climate model uncertainty. Big is bad. That's root mean squared error. So the bigger it is, the worse it is. And you're looking at the Chinese model, some NASA models, the National Center for Atmospheric Research, the Germans, the French, the Russians, the Canadians, the Norwegians, and yes, all the way up there is GFDL's two fabulous models, 2.1 and 2.0. Now, they've gone much past this now, but these models were the ones that really set the stage for some of this amazing work that's come after. So why did I have to start thinking about going back to the ocean and getting more measurements? Because look at the ensemble observational uncertainty. Oh, we're there. The models are so good. The ones I work with are so good that we're basically down to the uncertainty of the observations, which means if we want to improve the models so that we can tell when things are going to happen on planet Earth, we've got to improve the obs. And boy, I did not look forward to going back to sea and doing, measurement by measurement. You have to imagine me as a young grad student sleeping in a beanbag on a floor with a watch that beeped every 15 minutes to tell me to change the titrator. And it was really hard work and incredibly time intensive. So we have an option. Okay. So just to show you, here's the zonal winds. Is it working? So, yay. Okay, so the observed is on the left, and on the right is a whole bunch of models. This is just one metric we use to evaluate. But remember how important I told you those winds are and the Poleward Shift? Well, some of these don't get them quite right. That one's not so good. Okay, but some of them do really well. But this is how we evaluate. We look at these really carefully. And it's not just that. How about ocean heat content? We really need to know because we live in Arizona. So here's the observed on the left, and here is the Japanese, the German, the Canadian, and yes, there are errors, but we're getting closer and closer, and we watch this carefully. Now here's a challenge, dissolved inorganic carbon. How much carbon is the ocean taking up? Well, here's the observed on the left, and on the right we've got the Japanese, the Canadians, and these are looking harder. And I'll just say, the amount of data over here is really small. In fact, it's pretty darn small. So here's the nitrate, that upwelling of fantastic nutrients to the surface through the breathing of the Southern Ocean. So I want to show you just how little data we have. I know you won't believe me. This is all the data we have ever taken, ever, in the Southern Ocean by anyone. This is the nitrate. We put the little observations on there so you can see it, and time is ticking through down here. And what I'm going to simulate next is what would happen if we had biogeochemically censored floats. And we put in a proposal, me and some friends from Princeton and Scripps and the University of Washington, and we got it funded. But let me just show you what we project it's going to look like. These are the floats coming on now. This, robot floats, is how we're going to measure the ocean, how we're going to figure out what's happening and how it's changing. This is the new picture of oceanography. It's a revolution. We are going to change the world. No, really. So 2 years ago, in fact, just 18 months ago, 2 years ago we got it funded, 18 months ago we started the project. Southern Ocean Carbon and Climate Observations and Modeling. And it's NSF is the main funder. It's 21 million plus a little over 6 years. And then NOAA bought half of our floats, the actual floats themselves. Fantastic. And then NASA bought us all the optical sensors to put on all the floats, which was also fantastic. If it sounds like we wandered around with a hat begging, it's because we totally did. But this is so cool. Everybody said yes. Woohoo! So, if you want to check us out, here we are on the web, Southern Ocean Carbon and Climate Observations and Modeling at socom.princeton.edu. Very sorry, we couldn't get them to base it here. I'm only in charge of the modeling part. My friend Lynn Talley is in charge of the observational part. She has to deploy all these darn floats. She's at Scripps, and the directorate is actually at Princeton with Jorge Sarmiento, which is wonderful, but it would be nice if it were here. So here's the BGC Argo floats. This is what they look like. They're about as tall as me, maybe a little taller. And this is a little video of what they do. So the float starts, we deploy the float, and we have to calibrate all of these because, of course, they have fabulous pH, nitrate, and oxygen sensors. Not just temperature and salinity to look at the heat and fresh water budgets, but actually carbon. This is amazing. So the float sits at 1,000 meters, and every 5 to 10 days, it drops down to 2,000 meters, 20 football fields down, and does a full profile of measurements all the way to the surface, and it beams the data back in 12 minutes at the surface by an Iridium satellite. And just by the way, all of that data is free and available within 2 hours of when we get it back on land, on the web. You want to check it out? Come on in, the water's fine. No, really, come on in. Seriously, science fair projects, you name it. I'm expecting all of this. We've actually got little sponsored floats now where kids' classes pick a float and follow it around, do little research projects on it. It's awesome. But let me see if I can get this to. So here's the results. This is actually a cruise we did right before. So there was a little bit of a saga. This was supposed to be a Science and Technology Center, which is NSF's big flagship program, and then we wouldn't have gotten 21. We would have got $50 million. That would have been great. And we were selected as one of the 5 that were going to be funded. And then the sequester happened, and they said, oops, not you guys. I had a hard time getting out of bed during July that year. Oh, really? So disappointing. But we didn't give up. And in fact, we finally got the NSF to fund it anyway, the hard way. So this was one of our early cruises. And this is right here, see New Zealand? And what we did was, here's the temperature from the ship. And each of these is the temperature from the float that's been deployed from the ship. And down here, here's the pH from the ship. And each of these tiny profiles is a profile of pH in the ocean from our floats. Amazing. We have never had seasonal pH. We're actually watching the acidification of the ocean in real time, actual real time. And nobody's even there. And just by the way, there's Hannah Sinowski, who is a Wildcat for life. Woo! She graduated with a double major in physics and math and did a NASA Space Grant Fellowship with me in my lab, and she's now advanced to her doctoral candidacy at Princeton, and she deployed our first batch of floats off of Cape Town, South Africa, and there she is with one of the floats. Amazing. Arizona changes the world, I tell you. These students, the students at the University of Arizona, are amazing. I am constantly inspired by their go-getter, never take no for an answer, bear down spirit. It is amazing to watch them go. You just have no idea where they're headed. You just have to let them rip. So we're assimilating all that data into an ocean model, including all this carbon and biochemistry, and this is really important. And by the way, these climate models are now getting down to these really fine, 4 to 10 kilometers in the ocean. These very fine, so that we can get better projections at finer resolution. So we're now able to take our assimilated data and actually rigorously test our very fine climate models. And this is important because, here's just a little glimpse of what one of these looks like. This is the GFDL CM2.6 ocean simulation. That's New York City. You'll see what New York City pixel looks like, and then you'll see what a pixel in the ocean looks like for this model. And that's math. Woo! Isn't that cool? That's not a satellite. That's actually math. Fluid dynamics. Woohoo! If you've got kids or grandkids, tell them to keep up with their math. They don't have to get an A. A B will do. And then send them to me. We'll put them to work. It's fabulous. That's the Gulf Stream you're looking at here, going off into the North Atlantic. And I could show you an El Nino, but I've been dragging here. So the Poleward Shift in the models of the westerly winds says that we're going to take up more heat into the ocean, we're going to take up more carbon, and that it's the Southern Ocean in the blue that's doing the heavy lifting in both of these cases, which is really exciting. This is work that I did a while ago. But we like all the models. You saw some clunkers. You know, I wish we had a Cash for Clunkers program for models, but we don't. So all of the world wants to do their own climate model, and of course, they are all welcome to do so, but we're going to actually do this world climate in support of the next CMIP 6 we are going to actually try and encourage everybody to do a Southern Ocean model intercomparison project. And Ron Stauffer, who's here, is actually helping me lead this effort to get everybody to improve their Southern Oceans, because of course it's one of the most important things that will affect us over the next 20 years. So we're working on that, but here's where it gets, here's the what do we do about it part. Okay, because the ocean seems remote, but in fact, this is really cool. Really, just it won't work for me. So we have this Paris Agreement. We didn't have one even a year ago. 195 countries. I think the only one that didn't sign was North Korea. Seriously, it's such an improvement over where we were before. This is an opportunity because they are talking about, and this is built out of the United Nations Framework Convention on Climate Change from Rio de Janeiro in 1992, where they said that stabilizing greenhouse gas concentrations that would prevent dangerous anthropogenic human-induced interference with the climate system. And these are the gases that are covered, and this is mostly CO2, but about a quarter of it is other things that are important, but I'm mostly going to focus on the carbon here. And I'm on this Carbon Cycle Science Steering Group, so we've been able to actually start talking to the funding agencies about what needs to happen next. But what we think we need to do is actually try to verify these carbon agreements. This is what is next, and we think we can do it. There are two ways of looking at it: bottom up, which is estimating the anthropogenic emissions and removals based on socioeconomic statistics, and self-reported. Okay? And then there's top-down, like a constraint, a global constraint on the emissions, and it's based on atmospheric and/or ocean measurements of the gases and models of air and water flow. So US emission estimates are pretty good. We know it to plus or minus 3%, and we do it from calculating the mass of fuel, measuring directly at the stack, and looking at actually people's, our lovely energy companies' quarterly earnings. No, really. But we're actually pretty good. In other places, we learned that China had actually underestimated their coal emissions by 17%. And they self-reported that they had underestimated it. But that means that the ocean and land sinks were much bigger than we thought they were, because we knew that it wasn't hanging out in the atmosphere, so it went somewhere, and we missed it. I think we need to do this better. So the global carbon budget is divided by the Global Carbon Project, which is a European and US, but mostly European initiative, into these different components. The sources are the fossil fuel industry, fossil fuels and land use change, and the sinks are the land, atmosphere, and ocean. But there's a trick to this. So here's our sources: smokestacks, clearing trees, and then we know where that goes. Atmosphere we measure really well. I'll point out plus or minus 0.4 gigatons of CO2 per year. That's excellent. They do a great job. In the ocean, it's 1.8 gigatons of CO2 per year. That's nowhere near as good as we know in the atmosphere. And then we actually, and this is horrible, the land sink is actually calculated as a residual. We only infer what the land sink is from what we know about the atmosphere and the ocean and the emissions, which means verifying a carbon agreement at this point would be very, very hard. Okay, I'll just say not possible. We need to do something better. We need to know this better. So here's the increase in the industry emissions. And I don't know if you can see it, but the uncertainty has actually grown with time, which is what you'd expect when people are self-reporting. Land use change has not changed in the uncertainty. But here, big uncertainties in the past, but in the atmosphere, they've gotten much, much better. In the ocean, we have not seen much improvement. Really seriously. Not in a long time. Why? Because we were stuck with ships. Ships are wonderful and absolutely essential, but it takes individuals. You know, each cast that we do, you can only do 3 a day because it takes 8 hours, 4 hours for it to go down and 4 hours for it to come up. And then you can move to the next station, 4 hours down, 4 hours up. So 24 hours a day running around the clock, a ship can only do 3 profiles. And by the way, a ship costs about $45,000 a day, bare boat, and that doesn't even include the scientists and all the gear. If it sounds like I obsess about this, it's because I do. So one of my little handy-dandy floats that we were talking about, the bare float would cost me about 25 grand. And to deploy and calibrate one of my biogeochemical floats with the carbon costs about 100 grand. 100 grand. That's a lot, isn't it? But that 100 grand float will last me 5 years and give me a profile every 5 days. So in fact, it would pay for itself in less than 6 months, right? 6 months. And then it's got 4.5 more years of profiles to do, right? Excellent. 2 days of ship time gives me, you know, a float. That's it. Amazing. So I think we can do this. So what I want to do is change the equation. The atmosphere plus the ocean is equal to these other components, which I'm going to shove. Just by the way, they're all located in the same place. Where? Emissions, land use change, and vegetation are all on land. That 30% of the world that I don't study. Okay. So this makes it really cool, because if we do that, if we shove them all onto one side, then the uncertainties that I have to reduce is 0.4 plus or minus 1.8. So my uncertainty on all of this, which I would need to know for these carbon agreement verification, is plus or minus 2.2, not that much bigger number that we had from the inferred flux. So I like this. I like this. How could I reduce that 2.2 even more? Because really, 2.2 is not good enough. I'd love to see that at 1. 1 is what I want, 1 gigaton. So that'd be 0.4 from the atmosphere, 0.6 from the ocean. What would it take for me to get there? Here's the standard deviation of the monthly mean CO2 flux in the ocean. This means how hard would it be to measure this? How many floats would I need to actually get the error from that 1.8 gigatons of CO2 per year to something less? I need to reduce that uncertainty. So here is an animation of deploying my fabulous floats into the ocean. And what you're looking at up here is the number I'd have to have and the reduction in that 1.8 error I get. It's a fabulous observing system simulation experiment that Matt Maslow and I did to calculate how many we'd need. And in fact, we get, so we've gone from 1.8 to 0.98 to 0.95. Here, and this is, right here is just 500 floats. 500 floats. 500 floats at 100 grand each is 50 million, but remember, we're going to split this with the Europeans and the rest of the world, so it's 25. And remember, we only have to deploy a certain number every year, so that's divided over 5 years. So what are we talking? For 500 floats, that's $5 million a year. $5 million a year to reduce our uncertainty in carbon. I got to tell you, this is like the cheapest bang for the buck you've ever seen. I mean, really. So we ran this out. How far would we have to go to get it down to 1? And this is how many. It would take roughly something like 900 to 1,000, not the 500. So it's really not really 5 million a year. It's more like 10. More like 10 million a year. All right, so we don't have that money yet, but we do have a global agreement. 2 weeks ago, I was in Villefranche for the first workshop with 9 of the 10 major float deployers. And we have an agreement now for a global biogeochemical, what we call Argo array of floats. They're going to do half, we're going to do half, Europe is going to do a quarter, and the other non-European countries, Japan, Korea, China, et cetera, are going to do the other quarter. So, for treaty verification, we need to verify self-reported emission estimates. We need to establish baseline emissions. We need to account for changing land and ocean sinks. So what I need are more of these floats plus satellite-derived CO2. Oh, and I'm sure most of you already know the answer to this, which is, we already have it! Woo! OCO2. Now, okay, OCO1 did end up, woo, into the drink. Which was so disappointing. But OCO2 is up, and the first batch of data came out in September. It's so exciting. So we're going to have spatially varying from satellite distributions of CO2 that we can assimilate with our new ocean OBS and our fantastic atmospheric OBS that Dave Keeling started into a global data assimilation for carbon treaty verification. So 5 years ago, we didn't have a carbon-observing satellite. We've got one. Earth system models that do conserve carbon, we've got them. BGC Argo floats, we've got them. And an international political agreement to address the carbon cycle. We have all the pieces. Time to do it. Thank you. And that's it. This is what we'll be doing over the next 5 to 10 years, right here at the University of Arizona. Thank you.